Another way to describe orientation is through a method called the Euler axis formulation. And this was developed by Euler and published in 1775. And sometimes this formulation is called the eigenaxis formulation. So I'm going to try to demonstrate it here for you. Remember that we're talking about orientation of an object or an aircraft relative to an Earth fixed coordinate system. Okay, so what I have here is I just have this block of styrofoam, and it's just sitting on this table aligned. We're going to say that that's aligned with with due north. Okay, so imagine that there's a coordinate system attached to the table that's pointing straight at that wall there. And what I want to do is look at how I can orient this block of foam relative to that coordinate system. So remember that the original coordinate system is attached to the table, and now I want to figure out how I can orient this block of foam relative to that Earth fixed coordinate system. So what the Euler axis formulation does is it says that we can put an axis. I'm just going to use this piece of wire here to represent an axis. I'm going to push it through the origin there. And now if I rotate this block of foam, I'm going to hold the original axis in the same direction here. And then I'm just going to rotate this block of foam about that axis. And you can see that I can, just by rotating it, I now have some orientation that's different than that original axis. And it turns out that if I move this axis, I'll try another one over here, and try to hold that fixed, and then rotate the block of foam about that axis. You can see that we can get any orientation we want, actually, just by choosing the correct axis. So if I just put this straight up and down and rotate, then of course it's just going to rotate from north to south. It's just going to rotate in this horizontal direction here. So I can get actually any orientation of this block of foam relative to the original by just choosing a specific axis and then rotating it by some angle. Relative. So 0 would be back at the original coordinate system. And then when I rotate this about that axis by a certain angle, I can get any orientation I want by moving the axis and the angle of rotation about that axis. So that's the basic idea of the Euler axis. And one of the interesting characteristics of this formulation is that the original axis has the same coordinates in both coordinate systems. So let's just put this in at some angle here, and notice that this axis could be defined in x, y, and z coordinates, right, to get the direction of this axis here. And after I rotate the object, that axis actually has the exact same coordinates in the body fixed coordinate system or the Earth fixed coordinate system still attached to the table. So this axis actually does not change. It's defined by the same x, y, and z components in either of these two coordinate systems. So we're going to look at this mathematically now and see what this tells us. So let's look at this Euler axis formulation mathematically now. I'm just going to try to draw again real quick what this formulation is. So we have an x-axis, y-axis, and z-axis in general, and we can choose some Euler axis here, and that's going to have components x, y, and z. So we're going to call this ex, ey, and ez, and then we're also going to have some rotation angle about that, and we're going to call that capital theta, actually. Okay, so that's the angle that we're rotating about that axis, and the components are ex, ey, ez. Well, this actually gives us 4 components that define only 3 degrees of freedom. Remember, orientation only has 3 degrees of freedom from orienting from one coordinate system to another. So that means we have one level of redundancy. And so what most applications of this use one final equation. They say that the length of the Euler axis has to be equal to 1. So they make the length of that axis equal to 1, and that gives one additional constraint. And so this is it just has one redundancy equation here, basically, or one equation that's going to give us enough constraints to cut this down to a single solution, okay? Because otherwise you could multiply this Euler axis by any constant and it would make the axis longer, but you would still get the exact same orientation, okay? So this is just a constraint that we place on this in order to give us a single solution and bring us back to only 3 degrees of freedom to define our orientation using an Euler axis formulation. Okay, now one thing that I mentioned in the video is that the Euler axis components in the Earth fixed coordinate system F are equal to the same Euler axis components in the body fixed coordinate system. Okay, and so we're just going to call these EX, EY, EZ because they have the same components in the Earth fixed or the body fixed coordinate system. That's one of the things that's a little bit unique about the Euler axis formulation and kind of a cool property. Okay, so using this, we can use what's sometimes called Euler's formula to rotate one vector from one coordinate system into the other. So, for example, here we're rotating from the Earth fixed coordinate system to figure out the components in the body fixed coordinate system. If you know EX, EY, EZ, and theta, the rotation angle about that, then you can compute the components of one vector that we know on the Earth fixed into the body fixed. So, for example, we would use this this transformation to figure out what the weight vector is on board the aircraft, right, based off of its orientation. In the Earth fixed coordinate system, that's always pointing towards the center of the Earth. So we know what that is, and then based off of this orientation from the Euler axis formulation, we can figure out where the weight vector is pointing on board the aircraft, okay? Now, one shorthand notation that is being used in this equation is that EIJ, so we've got these, you can see EXX, Y, XY, XZ. This is just some shorthand notation where EIJ is equal to EI, EJ times 1 minus cosine of theta, of capital theta. Okay, so the capital C's here are cosines and the capital S's are sines of theta, okay? So now the inverse, if of course this goes from the Earth fixed coordinate system to the body fixed coordinate system, well, the inverse of this transformation we can get by using just the transpose of this matrix here. So we could go from the body fixed to the Earth fixed by multiplying the body fixed by the transpose of this equation. Now it just so happens that that is equivalent to using the negative of this angle, okay, of theta. So we could actually plug in negative theta instead, and get the inverse or the transpose of this matrix here. And you can see that actually because the negative of a cosine of a negative theta is equal to cosine of the positive theta, right? So actually this term would not change, this term would not change, and this term would not change. But you can see sine of a negative theta, we could also just bring that negative out front, and it would be equal to minus the sine of theta. And that's actually the term that's right here. So these two terms are equivalent except for the sine of theta. And so you can just change the sign, that to a negative and that to a positive, and that's the same as flipping the sign of that theta. And by sign of theta, I mean SIGN of that theta. So anyway, just by putting in a negative theta instead of a positive theta, we get the transpose, and you can work through each of these. You can see that that actually does create the transpose of this matrix here. So that's another cool property as well. Okay, so now we know how to use this using Euler's formula, and I'll just write that down here. Using Euler's formula, we can get this rotation matrix from one coordinate system to the other, and we can go either direction, from body fixed to earth fixed, or earth fixed to body fixed. And now what we need to know is the change in our Euler axis as a function of rotation rates on board the aircraft. And so so this is what we get for that. Let me scroll up here a little bit and make this a little bit bigger. Okay, so now you can also compute the change here in the Euler axis formulations. So the change in theta and the change in EX, EY, and EZ, and that depends on the current orientation of the aircraft, the current Euler axis, and the rotation rates on board the aircraft, P, Q, and R. Okay, so we can use this here to figure out what the change in the Euler axis for, or the orientation is as a function of time. And again, we're using some shorthand here that I'll fill in. So so we've got these EXX, and there's a prime here, and that's just to denote that it's different than these up here. So so EIJ prime is defined as minus EIEJ cosine of theta over 2 divided by sine of theta over 2. Okay, so you can see a lot of those terms show up in here. Cosine of theta over 2, sine of theta over 2. They show up right in here. And then in all of these prime terms as well, we've got the cosine theta over 2 over sine of theta over 2. Okay, so anyway, this completes the Euler axis formulation, and you could use this in flight simulation. The problem is that it still has a singularity. You can see that we've got a sign here in the denominator for this change in our Euler axis as a function of time. And anyway, so this sign in the denominator is a problem, because anytime the sine of theta over 2 is 0, then this is indeterminate, this matrix here. And that happens, unfortunately, when the aircraft is pointed due north or due south and is perfectly horizontal, which happens quite often compared to in the Euler angle formulation. We have the gimbal lock issue when our nose is pointed straight up or straight down. Well, this is when your nose is pointed aligned with the original x-axis or 180 degrees from that, and you're level. So this is actually a bigger problem. This gimbal lock problem that we see here, this indeterminate solution here, is a bigger problem, because this is actually a case that we would encounter more often in traditional aircraft flight than a traditional gimbal lock issue that we have from the Euler angle formulation. So actually, it's very rare that any flight simulator would actually use the Euler axis formulation. The reason we're talking about it here is because it can be used with a change of variables for another formulation called the quaternion formulation that is free of gimbal lock. And so that's what we'll discuss next.